Now we have a basic introduction for the high-speed busbar transfer device 7VU. So we talk about the basic logic, and we talk about afterwards the wiring connection to the device. And in the end, I would like to show you one slide for the cooperation between 7VU and the protection devices. So this is the HSBT function. The HSBT function has its own function group. So that means in their own function group, we have different function blocks for the function himself. So that means the function is integrated in the ZProtect 5 platform. So you can choose that. You can instantiate the function 4 times per device. And then you find the different function blocks, which are responsible for example, for the ready and readiness check, for the sensitive start types, for the blocking logic, for the transfer sequence, and in the end, for the algorithm for closing. Now we start with the readiness and unreadiness check. Why a readiness check is so important for an HSBT system? Because we need to be sure that this transfer direction is available. Otherwise, the device cannot transfer the load from one feed to the other feed. And here we have a normal industry application. So you see here, there is 4 different transfer directions possible with this 3-breaker application. So, and if we have a fault, we want to transfer the motor load from busbar 1 to busbar 2, for example. And afterwards, if the fault is clear, we want to switch back to the normal operation. And therefore, we have to define the different transfer directions. Now we have a closer look to these kind of normal operations, so the expected transfer direction in this application. So the following transfer direction shall be activated in the device. You can instantiate the transfer direction by putting some transfer directions from the library into the project, and then you define from which direction you want to switch. That means here from in-2 to busbar 2, from in-2 to busbar 1, or from busbar 2 to in-1, and so on. This can be defined in Dixie. So, and then we need to check, or the device need to check, which kind of application or which kind of transfer directions is ready or unready. In that application, therefore, we're checking the status of the circuit breaker. So that means we know at always when the circuit breaker is ready, when the circuit breaker is closed, and which kind of direction is available and which not. For some circuit breaker, we send open commands. For some circuit breaker, we send close commands. And other circuit breaker, like the tie CB, for example, needs to be supervised to know, okay, this CB is closed, that we can switch from here to there. And all these CBs or circuit breakers and their status and their task can be defined in Dixie. And of course, we talk about ready and unreadiness. So ready means ready for transfer. Unreadiness means we are not ready for transfer because of a missing status, because of a missing voltage, because of other issues. So if we have a fault, for example, in a faulty incomer, in incomer 1, then we have the following status. That means CB1 is tripped, CB closed, the intersection CB, the second infeed is closed, and the intersection CB is closed as well. So that means we deliver the energy from the second infeed, from the alternative infeed to the whole busbar. So, and in that case, of course, our device said, okay, now the transfer was initiated successfully, and now all the transfer directions are unready. Why? Because the fault is not cleared yet, and therefore the HSBT functionality is blocked. So if the fault is cleared, then of course one of the direction is ready again. So that means we can switch back to the normal operation. The second example here, we have a normal operation in the industry. where the CB1 is closed, the CB2 is closed, and the section CB is open. And we want to transfer the load from one infeed to the other infeed by closing the CB3. So, and this, of course, can be done by activating the transfer direction in comma 1 to in comma 2, in comma 2 to in comma 1. So now we have a closer look here. So that means we want to transfer the load from in comma 1 to in comma 2. That means this direction is ready. So that means we need to close here the tie CB to do that. The other way around is unready, so that means we can only switch in one direction. So after the fault is cleared, we want to switch back, and this can be done manually, that we come from in comma 2 to in comma 1 to come to the normal operation. This was very shortly the reliability of the ready and unreadiness check of our firmware. The multiple sized start types is the next topic. We have implemented different multiple sensitive start types into our HSPT functionality. For example, we have the electrical fault start, which can force by a binary input. And this binary input can be used by sending the trip commands, for example, from a transformer protection or from a line protection. We can have a problem in a control system, for example, the cooling system of a transformer or the cooling system of a generator. This is not an electrical fault start. This is a mechanical fault start, for example. And therefore, we can also use a binary input to start the transfer by a trip of a boiler, of a turbine, or of a control system for the fans of the transformer, for example. Then we have a start type which is called inadvertent open start. This is used when the local CB opens unexpectedly. This can be, the reason can be a misoperation, and therefore we detecting the CB open position and we combine it with the incomer current to be sure this is not a fault. This is by opening the CB. The other topic or the other reason could be also a remote CB is opening. For example, this could be the CB here, so where we have no information from the system. So we can use the first solution is the possibility by using a binary input or using the additional start criteria to initiate a transfer. The second solution is that we can use here the undervoltage on the motor bus or the underfrequency start to detect that the device can be detect itself that the condition undervoltage or underfrequency is there and we have no currents on the incomer. You see, the current transformer on the incomer is very important for the HSPT device. And of course, the underfrequency start is more sensitive, and we use that in case of an inadvertent open of a remote CB, so where we have no information about the auxiliary contacts. For example, we have a fault start type or multiple sense start type for when we have a fault on the main infeed. One possibility is as well the binary input to trigger the electrical fault start. Another possibility is as well, again, the undervoltage start or the undervoltage, the underfrequency start on the motor bus. So at both solutions, we can start a transfer in case of a faulty main infeed. And if the fault is cleared, then we want to switch back to recover the, recover incomer. And this can be forced by a manual start. And this is detected by a binary input for the signal manual start. So now we know the different sensitive start types, and now we could look back to our application here with the 3-breaker application, and we have the following transfer directions. And these following transfer directions can be set as automatic transfer directions and as manual start only transfer direction. And that means for the recovering of the incomer, we only should use manual start, because the transfer then is done manually, and we can do it by paralleling. If we have a closer look here to that application, the second application, then of course the TiCB is closed. We want to switch from incomer 1 to incomer 2. These both transfer directions. The first one is the automatic key start caused by electric failure, for example, and the switch back after recovering, then we can do it and we can force it by manually. Come we to the blocking logic, and the blocking logic is also important, is also important for the HSBT function, because we do not want to transfer in case of a fault. In case of a fault on the local bus bar, we do not want to do that, because normally we detect the voltage is going down, and in that case there is no need to transfer because the fault is on the motor bus. And in that case, we need to block the HSBT function. We can do that with the combination of the current on the incomer. We have a special implemented fault detection for that. This function blocks picked up internally and block the under voltage criteria. Or we have the possibility to initiate here or to force this binary input to block the whole HSBT function. And this can be done by an external tripping command from an overcurrent device, for example. Or for the next topic, we can use as well this kind of what I said, the fault detection, and this fault detection is blocking the HSBT function until the trip is cleared. And this is working for the under voltage, under frequency, and CB inadvertent open start condition. So that means if we have a fault on the bus bar, the HSBT device is blocked because we can't transfer the load from the faulty bus bar to the healthy system. If we have a faulty motor, for example, then in that case, we also do not want to transfer the load, because the fault location is here, and we can open the breaker here. And of course, we need to detect that we have a faulty motor, and the protection device is tripping the breaker here. And we need to block, because if the fault is here, then the voltage goes down. We have to block the under voltage criteria. And of course, the fault detection function will detect this problem and block the under voltage start. Additionally, we have the possibility as well to use here the binary input, as I said before. And if the fault is cleared, for example, the voltage comes back on the motor bus, and we have no start triggered, then everything is fine. So if we have, for example, a problem with the VT connection, that the VT, PT or VT is broken, we have a broken wire, and we lose the voltage signal normally, then we have as well here also a busbar voltage which is directly going to zero. And for that, of course, we also need to block the HSBT functionality. And this blocking logic and the failure detection of our functionality is detecting these, and is blocking both criteria that we do not initiate a transfer from one feed to the other feed. Or the same example with the VT, the MCB is open. So, and therefore we can use the binary input that the MCB is open, and this binary input or this signal will also block the under voltage or under frequency start. And this is also used in a fault detection, so that in the end the transfer, the HSBT function is not transferred the load from one to the other side. Then we have some cases where is not a fault happened. For example, CB is withdrawn or CB is under test. So, and for that, of course, in a medium voltage switchgear, we also need a signal to block the HSBT. And this is normally done by a binary input. Then when the CB is in withdrawn or the CB is in a test position, then we can use that one to block the HSBT before we do some manual operation on the circuit breaker. And finally, if we have some manual open on the circuit breaker, then we also want to avoid that the transfer is initiated, and of course, therefore, we also using here a binary input on the device to block the HSBT functions. And this is important because you have to do that at any time when you want to do some manual operation on the circuit breaker. Then please activate the blocking signal for the HSBT. And for example, if a motor is started, then we will see on the motor bus that the voltage is going down. So that means we have a voltage drop there. And this is a normal use case when the motor is started. And therefore, we also want to avoid that the transfer is, the HSBT is transferred the load from the main in-feed to the alternative in-feed. And therefore, we also detecting these by using the incomer current. And then we block the under voltage start criteria. Yeah, and finally, we can also have some power dips in the main grid. And this also do not, with that, in that case, we also do not want to transfer. We have the blocking logic, which is connected with the incomer current, and also we have the possibility, in case of a voltage drop, that we block the transfer. So this is very important. If we have a very light load on the motor bus, then we do not want to transfer. And in that case, if we have a light load here, so we do not measure so much current here, and therefore, I would say the implementation of the release logic avoid an unexpected transfer. So then we have the case of an abnormal CB position. So it could be that the CB is in the intermediate position, or it could be that all the CBs are closed. So in both cases, that when we have an abnormal CB's position, the transfer should be not initiated. So that means all the transfer directions are unready. Or in the very seldom case where the device is in an error state or the function is in an error state, the HSBT will be inactive. So this was one overview about the blocking logic, which is already implemented. So that means from your side, there's nothing to add more. If you have some specific applications, you can do that at any time via CFC or via some additional blocking criteria. So then we come to the settable transfer sequences. And here we have a look back to the electrical fault start. And the electrical fault start means we have a fault on the incomer or on a transformer, for example. And mostly these kind of electrical fault start will initiated by sequential transfer, and that means open before close. That means we have to open the affected circuit breaker, and afterwards we have to close here the alternative incomer source. And this looks like this here. That means we got the start signal. The HSBT is giving the open command to the circuit breaker, and the position of the circuit breaker will be detected. Okay, the circuit breaker is open, and then we give, after a short action time, we give the close command to the alternative source, and the position will be reached after the closing time of the circuit breaker. For the busbar voltage doesn't mean that we have a short dead time. So this is the usual way how we transfer in a sequential mode. For example, if we have an inadvertent open of the circuit breaker, then we can do that also, or it is normally also sequential or simultaneous transfer, because the circuit breaker is already open, and then we can use here the simultaneous transfer. And for the simultaneous transfer, for example, we do it differently. So that means close and open command is sending by the same time. And you see it here. So that means we triggered by a non-electrical fault start, and the open command and the close command is sending at the same time. And we reach the position open and we reach the position close. And here you see the energization of the motor bus. We have a very short gap here, or drop here of the voltage on the bus bar. Of course, you can also use the simultaneous transfer for electrical fault start. So in some application, it is absolutely necessary to limit the voltage drop on the motor bus. And therefore, of course, you can use as well the simultaneous transfer for the electrical fault start. And for that, we need to consider the decoupling functionality, because when we send the open command and the close command at the same time, we need to be sure that the incoming breaker from the source 1 is open. And if not, then we need to trip the other breaker. So then, of course, we lose the complete motor bus, but it is absolutely forbidden that both breakers are in for a longer time. We also use the simultaneous transfer in case of a problem with the control system. So therefore, we can use as well the simultaneous transfer for the fault, if the fault is cleared, to recover the in-feed, or to go to the normal operation, switch back from an alternative incomer to the running main incomer. Then we always use the manual start, and this is done by a paralleling for a short time for the transfer. So, and this is used by the paralleling transfer. That means both breakers are in for a short time, and then we open the breaker. And this looks like this here. So that means we have a manual start command. So we have the close command for the breaker, and we have the open command, which is coming later. And over the whole time, the energy on the motor bus is supplied, and we have only a short window where we have both in-feeds connected to the motor bus. So as summary, we can say we have to set up a transfer sequence. You see, we can use the sequential in an electrical fault start, in a divergent open start, an under frequency start for the manual start, and for some additional start sequences. The simultaneously transfer can be used now as well in an electrical fault start, in a non-electrical fault start, under voltage, under frequency, manual start. And then we have some additional start criteria for the simultaneously. And in the end, the paralleling transfer is used for the manual start. So when we have a look now to the next point, and this is the algorithm himself, I would like to show you how the HSBT functionality is working. I think this is the very important part of this functionality of this device. Then we have as well here the same application as before. So the easiest transfer is the paralleling transfer because we have idle conditions. So that means we want to switch from one in-feed to the other in-feed, maybe for maintenance or maybe for shutting down the power plant or the system. So therefore, we have here, for this purpose, we use the delta angle, the delta voltage, and the delta frequency because between the two incomers. And these switching should be in the range of the synchronous or synchro check functionality. And this is the setting here for the paralleling transfer, which is well known from the synchro check functionality. So when we talk about the sequential transfer, then we have to think about the equivalent of the circuit, and then we see, okay, we have influence from the residual voltage to the reference voltage. The residual voltage is the voltage on the motor bus, on the motor, and the reference voltage is the voltage which we are measuring from the alternative source, for example. In that case here, we will have a difference between both because we are closing here then the breaker, and of course this brings some influence, and this needs to be detected, and this needs to be calculated and distinguished. So, and how does it looks like? I like this diagram very well, because here we see the reference voltage. This is the voltage which we are measuring here, and we see here the residual voltage of the motor bus. And over the time, the residual voltage becomes smaller and smaller and smaller, and also the phase angle gets bigger and bigger and bigger, and the frequency is going down. So this needs to be distinguished by the algorithm for the sequential transfer. That means we open the breaker first, then the voltage is going down. The voltage, the amplitude is having an exponential decay, and the frequency is decaying linearly, and also the phase angle from the residual voltage to the reference voltage lag behind the alternative or the reference voltage in that case, and the delta angle is increasing. So all this needs to be distinguished for the algorithm. So that means, as a note or as a hint, the parallel transfer can be used when we have a stable sinus wave, and the sequential transfer can be used when we have a decaying sinus wave. This is a note, this is a hint, and I think it is very easy to know that, to make the right decision. When we come to the next, so that means when we close the breaker. So we can close the breaker not at any time. So that means we have a small window where we can close the breaker in a fast mode or in a fast time. So after the voltage is going under 70% on the motor bus, we have no chance to close anymore in fast time. So that means we have to wait, or we have to wait until there's no voltage on the motor bus. And this is like an ATS is doing a transfer. Now we come to the guideline or to the standard, which belongs to the fast transfer. And this ANSI standard, IEEE ANSI standard C5041, it is written that a fast transfer is defined by a time period of 10 cycles or less. So, and the maximum phase angle between the motor and the residual and the equivalent voltage on the alternative comma does not exceed the 90 degree. And there's a relation between them. That means this will happen with the voltage per hertz difference of smaller than 1.33 volts per hertz. So this needs to be considered for the algorithm. Now we have a look here on the diagram on a snake here again. or snail again, not snake, snail, where we have different points where we can switch, where we can do the switching, or where we can do the closing. So, but you see here, we have different influence here on the differential voltage between the motor voltage and between the alternative in-car voltage. So, and then when we come to the first algorithm, or to the first mode, and this is the fast mode. Fast mode is in that window here. That means we have a very short window here to close the breaker. And therefore, you see the influence on the delta voltage between the reference voltage and the residual voltage is not so big. That means we have not a big delta angle, and we have not a big difference in voltage and frequency as well. And of course, these kind of fast mode can be activated in our device. This is the first closing algorithm. That means here in Dixie we have the possibility to activate this stage, and you have to set here the settings for the fast mode. And when we talk about fast mode, I mean very fast mode or ultra fast mode. That means under idle conditions, we can close the breaker, or we can give a closing command in a time of 10 milliseconds. The next possibility to close the breaker is the second part, or the second algorithm, and this is the algorithm which is used for the real-time fast mode. So that means we have two windows here. We have one window and we have the second window. That means the phasor is going in that direction. So then we go out. He is not allowed to switch because the phase angle is too big. And then we come slowly back, or we come back. And this is here the unsaved area. And this is, of course, here the saved area. So that means here in that both blue areas, we can close the breaker with the real-time fast mode, and therefore we have implemented the predictive algorithm to do the prediction for the voltage and the frequency and the delta angle at the closing instant. This also considering the closing time and so on of the circuit breaker, and this is implemented as a second stage here in our device. So for that as well, you find the second stage, RTF mode, means real-time fast mode, and for that you have to set here the settings. You have to switch it on. Here you find the voltage per voltage divided by frequency, the variation here, the 1.33 hertz or per unit value, and also the delta angle, the delta frequency, and the minimum voltage. And the minimum voltage is set as 70%. That means under 70%, it should not transfer in fast time anymore, because we need to, if we are under this voltage level, then we can destroy, or we can damage the equipment on the motorbus. So this was the second part. Now we come to the third part, and when we talk about the third part, then we talk about here these green pieces of cake here, this is the in-phase mode or synchronous mode. So that means our phasor is coming back. So it's turning 360 degree, and now we are equal to the reference voltage. That means the phase angle is quite small, and then we have the next time to give the close command. And then, therefore, as well, we have a stage here, and you can add this stage or can enable the stage, make the settings here. And then, of course, we have the possibility to do that in as an synchronous switching. So then we come to the fourth point, or to the fourth possibility to close the breaker. Here we talk about fast closing. Yeah, here you see, okay, this is here the phase angle of the reference, or the residual voltage to the reference. And this is the voltage difference here, or this is the voltage on the motor bus. You see here the dotted line here is the voltage and the frequency behavior. And you see here in the first part, we have the fast mode, as we talk about, and the real-time fast mode. And then we have the in-phase mode. And after the voltage is going under this 70% limit, then we have no chance anymore to switch back or to close the breaker or to transfer in fast mode. Then we talk about the residual voltage mode. And the last point is the long-term mode. And long-term mode is a time delay, which can set in the device. And of course, this is normally done when you're closing on a dead bus. And of course, the residual voltage mode is normally used, for example, in an ADS system. That means both residual voltage mode and long-term mode are backup mode for the IHSBT system. So then we have another view here on the transfer system, on the phase and sieve algorithm. You see the sequential transfer and the simultaneous transfer. That means all the modes are available for both transfer, sequential and simultaneous. And for the paralleling transfer, we're using the synchro check. And when we talk about fast, then we talk about fast mode, real-time fast mode, and in-phase mode. And when we talk about backup transfer, then we talk about residual voltage mode and long-term mode. And every modes can be activated in the device, and the device is doing the decision by himself, automatically calculated, automatically detected, and decided which kind of switching types they want to use to transfer the load. So, and this was a short overview over the algorithm for the closing signal, or for the closing functionality. Here is an overview about the whole functionality. This is what I already explained here. So you can check these afterwards, because you got these slides, and then you can check that afterwards. You see here, the manual start is usually used for switching on or switching off some generator, or to transfer the load from one infeed to the other infeed. Normally the recommended sequence for it is a paralleling. We have the abnormal start condition. This should be done simultaneously. We have the fault start conditions. This should be done sequential by electrical fault start or non-electrical fault start. And then we have the possibility to add some additional start sequences or start types for sequential and simultaneously transfer. And this is very flexible in Dixie. You can set these by the customer with a CFC or with an additional protection function. For example, for power plants, I saw there was a combination for simultaneously transfer within reverse power protection, for example. So then we have a short look here onto the user scenarios. We discussed all the user stories in my presentation. So you can go one by one, these user scenarios, and you get some recommendation how to set it. If you have a fault on the incomer, if you have a fault on a transformer, and so on. This is already, I think, discussed in the presentation as well. But here is I think it is a good overview for you when you do the engineering and when you do the selection of the device. Now we come shortly to the wiring connection, and this is important for the selection of the device. For the incomer VTs, you have to consider a phase-to-phase voltage. We also allow the phase-to-ground voltage, but it is not recommended in case of a phase-to-ground fault. Then the voltage becomes zero. So therefore, we always recommend the phase-to-phase voltage to be sure, okay, there is no phase-to-ground voltage on the incomer. And for the motor bus, here we have currently the implementation that we want to have a 3-phase voltage could be a phase-to-phase or could be also the phase-to-ground voltage as well. In the next version, we also get here a single-phase connection type phase-to-phase voltage for the motor bus detection. This is especially for retrofit applications very important. So, and why we have the decision, or why we use here the three-phase voltage at first, because the algorithm for the fast switching is based on a three-phase stable frequency measurement, and therefore we have this three-phase implementation here, and also some additional supervision functions like phase sequence and other supervision functions for avoiding any mistakes. If we have only the single phase connection types for the motor bus voltage, then of course we cannot provide this ultra fast switching time, because we have only one voltage to make the calculation for the frequency. And if we have a closer look here on the current transformer, the current transformer in the incomer are very important and necessary. Why? So we trigger, we need the current detection to ensure that we have under voltage or under frequency won't be triggered before the upstream CB is tripped by a fault. For example, we also used the current information as an additional criteria for the auxiliary contacts of the CBs, of the circuit breakers. Here there's something new here for the tie CB. There's no need to have a current transformer anymore, because we implement the function group without current, circuit breaker without current. And this is, I think, you can save some money here when you use the function groups without current, the circuit breaker without current. And this is a cost-efficient possibility to avoid any additional I/O modules here in case that you have a tie CB. So then, what we additionally need for the high-speed busbar transfer system is the auxiliary contacts of the incomers, the open command, the close command, also the auxiliary contact of the section or tie CB. And if you want to switch the intersection CB or section CB, you have to connect as well the open command, the close command for this section CB. And this is neat to define the right hardware selection for your application. So, coming to my last technical slide here, and this is a typical industry application. We have two incomers, two transformers, we have a section CB, and we have a fault on the motor bus. So, and we have one possibility to block the HSBT, and this is the blocking input. We have another possibility to block in case of a fault on the motor bus. This will be done automatically by the function himself, and after clearing the fault, the device or the functionality needs to reset. When we have a fault on the upstream or the downstream in the upstream infeeds, maybe on the transformer, then we detect these. We can use that as trigger for the fault start, and we can also use here the signal from the transformer protection, the tripping signal, to initiate a transfer. And last but not least, we will have also faults on the main bus or main source, and that will be detected by an under voltage start or under frequency start on the motor bus.